Good afternoon, guys. This is Professor David J. De Los Reyes. My topic this afternoon is an interesting topic. The topic is actually miscellaneous volumes. Okay, let's proceed. Miscellaneous volumes. I will give you an example on how to derive the formula of a certain figure, a popular figure, by using miscellaneous volumes. Okay, let's proceed. My lesson now is lesson 79 on my channel on the topic integral calculus under the subtopic volume miscellaneous volumes. Miscellaneous meaning it does not involve the circular disc, the hollow cylinder, or the circular washer. This miscellaneous refers to solids involving the edges to be straight lines. There are no curvatures. Okay, let's proceed. Problem. I will try to read the problem. Yesterday, I derived the formula for taking the volume of a right pyramid with a square base in altitude h. So for this afternoon, actually, the solution is just a simple one, but we do not know where it came from. Actually, the volume for a rectangular block is actually length times width times height, but not everybody knows that it emanates or it originated from integral calculus. It was derived from integral calculus. Okay, I will try to read the problem. Derived by integration, the volume of a rectangular block of length L and width W and altitude capital letter H. Meaning, we are given a rectangular block. Okay, this is length, this is width, and this is height. And the problem is asking that we shall derive the formula for taking the volume as a general equation. Actually, under lower mathematics, we always use that the volume of a rectangular block is actually length times width times height. But not everybody knows that this formula actually originated or emanates from integral calculus. It was derived from integral calculus. Okay, let's proceed. We try to figure out the rectangular block on the X, Y, Z plane. We are now in space. This is the x-axis, no, y-axis, x-axis, and this is the z-axis. Like what I have shown you yesterday, we are now on the XYZ plane. The first wall is actually the XY plane, the next wall is the YZ plane, and the floor section is actually the X and Z plane. So actually we are now in space. We are now considering figures to be solids, so actually we are not only considering planes, we are now in space. Okay? If we try to figure the rectangular block on the XYZ plane, the configuration will be something like this. You should graph it correctly. This is W, this is length, and this is altitude h. Sorry for this one, guys. I put a small letter h. It doesn't matter. This is a capital letter H. Capital letter H. Okay? So if we now try to place the coordinates correctly, consider for the meantime, so you will not get lost. It will be something like this. Take one plane at a time. For the meantime, forget the Z plane. Okay? Just consider the Y and X axis. So actually we are on the XY plane. So if we try to place the coordinates of this on the XY plane, this should be Y0, this is XY, and this is WH. This one here is on the vertical axis, it is 0h. and the one at the bottom portion, this is actually the origin, it is 0, 0. So you will not get lost. If you, on the so-called placing of the coordinates, consider two lines at one time. It's for the first one, it's only x and y. Forget the z first. So we place the coordinates correctly. Okay. On the YZ plane, forget the x first. Forget the x first. Just consider the y and z. So it will be something like this. Okay. If you place the coordinate of this one, it should be L0. This is LH. For z, it behaves like an abscissa. It's a vertical, or it's a vertical distance. Okay. So actually, why this is L0? Because from this here to this point, the distance is L. So if we try to designate the coordinate of this, it will be L0. The upper one, it will still be L, but with a certain height with respect to y, and it's h. Okay, so this is coordinates L and h, this is L and 0, considering the y and z axis. Forget the x first for the meantime. Okay, so we now we have already placed the rectangular bracket on the xy plane. So if we try to take a differential slice, this one, okay, this is rectangle. We take a differential slice. If we bring it out, it will be something like this. This length here is this one. This length here is this one. And the thickness is dy. And I place it here. This length is actually ZL minus CR, and that is actually equal to L. This one. Luckily for a rectangle, this length is not variable. Luckily. Okay? From the bottom portion to the value h, as it goes up, this length here does not change. So actually CL minus CR is just simply L. And for this length here, it is XR minus XL. And luckily also, as this differential area moves from 0 to h, it does not change also. So actually XR minus XL is equal to W. And the thickness is dy. And the proper way to, what do you call this, imagine this one, how I derive CL minus CR equal to L, it will be something like this. Okay, just consider this portion. Forget the x-axis for the meantime, just take this portion. If we try to take the differential slice, at this point here, there is z and y. Okay, the one on the right, I put it as CR. The z on the left, I put it as CL. Okay, as you can see it, ZR is actually a vertical line. And ZL is also a vertical line for a rectangle, luckily. And the equation of CL is actually equal to the length. From the origin up to this, this is L, the length of the rectangle. So actually CL, C sub L is L, and C sub R, the one on the right. Okay? It is on the y-axis, so CR will be 0. It is this. Okay? For this portion here, forget this one, it is this. You go to this side, consider for the meantime the y and x. Forget the z. There is an xy here, there is an xy here. The x here is actually xr. And the x here, I place it as XL. And actually, the XR is actually a vertical line also. This is a vertical line. Because as this differential area moves from 0 to h, it does not change. It is a straight line. And what is the equation of that? XR is equal to W. Why W? Because the distance from the origin to here is W. So XR is equal to W. And what is the equation of this vertical line here, the one on the left? It coincides with the y-axis. XL is equal to 0. The value of the horizontal distance is actually 0. This one, XR is equal to W. So actually, the difference of XR minus XL is actually this one. For some other problems, this distance here and this distance varies, but for a rectangle, it does not vary. It is just simply straight line. So I place it here, CL minus CR is L, XR minus XL is W, and this is the thickness dy. And as you can see, this thickness dy moves from 0 to capital letter H to cover up the total distance of the rectangular block. Okay, let's try to solve the base area. The area of the cross-hatch in red is actually the base area. As you can see, it is the product of CL minus CR times XR minus XL. Length times width, or L minus 0 times W minus 0, or the base area. The area of the one cross-hatch in red is actually WL. Okay? And what is the thickness? Thickness is dy. So to compute for the volume of this one, it should be the base area times the thickness. Because this base area moves from 0 to H to cover the total volume of the rectangular block. You assume that this is the rectangular block and it moves from 0 to H. Okay? And luckily for a rectangle, the upright motion does not vary. Okay? It is just a pure constant because it is only vertical lines. Okay, I will place the lower limit. Lower limit will be 0. Upper limit is H. Because we are integrating with respect to y, okay? This y here moves from 0 to H to cover up the total volume. So our limits are actually lower limit equal to 0, upper limit is equal to H. Therefore, differential volume now will be equal to base area times thickness. Base area is actually WL, thickness is dy. This is now a differential equation. Okay? So to take the volume as the base area moves from 0 to H, okay, we move the base area from 0 to H, okay, to cover the total volume. We now try to integrate both sides. So the integral of differential volume equal to the integral from 0 to capital letter H of WL dy. But this WL here are constants. Okay, so it will come out, the integral of dy now will be just simply y with the limit from 0 to H. Okay, so this is WL times the quantity capital letter H minus 0. Upper limit, lower limit. This is now 0. Okay, it has no effect on the final formula. So the volume now for a rectangular block in terms of the length, width, and height is just simply length times width times height cubic units. So actually the formula we are using under lower mathematics under solid mensuration, in which the volume of a rectangular block is length times width times height. This is the origination. It emanates from here. Okay, guys? That's the derivation of the formula for taking the volume of a rectangular block using the so-called miscellaneous volumes. There are no circular things over here. It involves straight lines. So it could be a rectangular block, a square block, or a pyramid, or other things. Okay? Okay, good afternoon, Los Angeles.